Okay. Thanks to you guys for showing up today. I know it's the last day before the break. So we're going to pick up where we left off last time with viscous flows through pipes, namely when you get into turbulent flows. And this is going to be sort of a review for anyone, well, all of you that completed lab number 3. We're going to get into the background of that Moody diagram we used for lab 3 and discuss some of its usage beyond the pretty narrow application in that pipe flow lab. First, though, I want to recap or kind of wrap up what we were discussing in the previous lecture on Monday, dealing with turbulent velocity distribution. So we're going to try to keep today manageable through 3 objectives. First, we're going to conclude the description of shear stress and velocity distributions in turbulent flow. We're going to apply the energy equation and dimensional analysis to find head loss. And third, we're going to use the Moody diagram to calculate head loss in straight pipes. Okay. So we were talking about on Monday, we were talking about the turbulent flow through a pipe, right, which happens when you get over a pipe diameter-based Reynolds number of about 4,000. And one of the things that I concluded with was saying, unlike a laminar boundary layer, okay, where you end up with this parabolic velocity distribution, a turbulent boundary or a turbulent flow through a pipe looks a lot more like this. It's basically, let's see if this is the center line here. Okay. A turbulent velocity profile in pipe is much flatter. And the reason for that flatness is that because of these 3-dimensional fluctuations that occur in a turbulent flow, it's a lot good at mixing faster moving packets of fluid with slower moving packets, and so it pushes all that momentum out towards the walls. Okay? And so it's really only out here at the very edge of the flow, right, where it's in contact with the pipe walls, that you start to see this reduction in velocity. So let's, if this is a function of u of r, and here's r. So this is our velocity distribution. Okay. Out here is our pipe wall. I'm going to set up another set of axes here. We've got r, and here we've now got the shear stress. Okay. So from our earlier discussion of any fully developed flow, laminar or turbulent, we said that the shear stress, the total shear stress, has a particular kind of distribution along the radius of the pipe, right? And that was that it increases linearly with the radius. It's 0 at the center, it's the wall shear stress at the edge, and it's a straight line between those two values. Okay, so here's our shear stress. And out here, right, it's just the wall. And I also pointed out, right, I said that the shear stress in a turbulent flow is equal to, right, the laminar shear stress plus some turbulent shear stress, where the laminar shear stress is equal to negative mu du mean dr. Okay? In other words, we're saying if we take the average velocity profile, and we try applying our Newtonian relationship to it, we don't capture all the shear stress, but we do get this part referred to as the laminar component. And then this turbulent component is basically it's what we call the Reynolds stress, and that's what we assign to all of those velocity fluctuations that are causing this diffusion of momentum. Anyway, the point is, if we look at this term and we look at this velocity distribution, we see that there isn't a very large velocity gradient across most of the pipe. Okay. It's only out at the wall where we have a significant du/dr. And so we can draw a distribution then of the balance between the different types of shear stress in the pipe. And what this leads to is this idea that out here at the wall, the velocity gradient is really high, and so the shear stress is made up almost entirely of this laminar component. And so let me draw this a little bit. Okay. Here's the laminar component of the shear stress, and then here is the turbulent component of the shear stress. So turbulent, laminar. Okay. So now this sort of division into laminar and turbulent, we say out here, right, where the velocity gradient disappears, it's all the shear stress is basically turbulent, and out at the wall, where you have a high velocity gradient, it's basically a laminar. And so this leads to this division of the flow into three regions. Okay, so we're going to call this region 1, region 2, and then region 3. And so 1 is what we call the viscous sublayer. The idea here is that near the wall, turbulence is suppressed and viscosity dominates. Right? And so this is reflected by the fact that out near the wall, in region 1, almost all of that shear stress is made up of that laminar term. All right. 2 is what we call, 2 is what we call the overlap layer. Viscosity and momentum fluctuations, or momentum diffusion, are both important. And then 3 is what we call the outer layer. Okay, near the pipe center line, momentum diffusion is dominant. So all of this is to say that out in the viscous sublayer, tau laminar is much greater than tau turbulent. In the overlap layer, tau laminar is about equal to tau turbulent, or at least of the same order of magnitude. And then near the center line, in the outer layer, tau turbulent is much greater than tau laminar. So in laminar flow, we took this idea that we had a linear distribution of shear stress, and we said we know how the shear stress is related to the velocity distribution, and we got a parabolic velocity distribution from that. We can't do that in this case because we just don't know what this tau turbulent is, or how to relate that to the underlying velocity distribution. It can't be done. So we know, right? So the velocity distribution, we said last time that
right, u is equal to, right, some underlying average velocity plus a fluctuating component. We're never going to be able to get this part using a theoretical model, that fluctuating part. It's chaotic. Okay. Chaotic and unpredictable. So the next best thing is to try to come up with some sort of equation that can give us at least the underlying average velocity profile, because that's useful. That's what we use to get flow rates, etc. So we know that u of r, right, or u itself, right, is a function of, right, tau w, rho, mu, r, and in this case y, where y is r minus r, or the distance from the pipe wall. And we're going to skip the actual interim steps of the dimensional analysis, but this is what people have done, is that they've performed a dimensional analysis on this and done a ton of experiments, very carefully controlled experiments. And the characteristic non-dimensional equation that they've come up with is this. U bar over this thing called the shear velocity, u asterisk, we'll get into that in a second, is a function of y rho u asterisk over mu and y over r. Okay, so we've got this dimensionless relationship, and then lots and lots of experiments. They've come up with empirical correlations for this dimensionless velocity distribution. I'm going to flip over to some slides here to sort of show you what these look like. These are not things that we're going to do a whole lot with mathematically, but I want to introduce what you're seeing in the next time you see a turbulent boundary layer. Okay, so they've got this dimensional set of equations. I mentioned there was this u star, this thing called the shear velocity. Okay. The shear velocity, it's worth noting, is not actually a velocity. It's the wall shear stress over density to the 1/2 power. The reason it's called shear velocity is because it's got units that look like velocity. It's length per unit time. So what they've done is through the experiments, they've determined that there are really 3 regions of flow, right? We introduced those. The viscous sublayer, the overlap layer, and the outer layer. And each one of these obeys a different empirical relationship. Very near the wall, okay, in this viscous sublayer, the dimensionless velocity, okay, u bar over u star, is equal to the right-hand side of the equation. So over here we've got the dimensionless velocity, this what's called the dimensionless distance from the wall, okay? And this is in a semi-log plot, okay? So power to 10. This is in a linear plot, so this is that viscous sublayer right here. Then in the overlap layer, we have a different equation that's been derived from, again, experiments and empiricism. Okay, so we've got the overlap layer, and then in the outer layer, we've got another equation here. So these are equations that can be found in the book. I'll post this slide, but I simply want you guys to understand and take away from this that the turbulent boundary layer, or the turbulent flow in a pipe, the velocity distribution is really complicated. Okay, laminar, we just had an equation. It said it's parabolic. The velocity at the center line is double the mean flow rate, or double the mean velocity. That was something we got out of just doing the math. Here, we can't approach it using theory. We have to divide it into 3 sections. We have to say, all right, you know, the viscous sublayer, we can determine the thickness using this non-dimensional relationship of y star over mu less than 5. Then we have an outer layer, and somewhere between we have this overlap layer. It's really nebulous and kind of indistinct. And so this is one of the reasons that turbulence is really challenging. Okay. So we're going to loop back to this if we have time, but I'm going to move on now to, well, one last note here, actually. So there's if you don't want to get into that kind of sophistication in predicting the velocity distribution,
there's some really simple approximations that work relatively well. These are what are called power law profiles. So a really simple approximation is used, saying that if you've got the velocity at the center line, okay, it's called v sub c here, but understand that that's just the mean velocity at the center line of the pipe. That u bar over vc, so the non-dimensional sort of, it'll go from 0 to 1, can be approximated as 1 minus the dimensionless radius to the 1 over n power. And n, okay, is chosen based on the Reynolds number. So here's a graph showing the value of n that's been empirically found for different values of the diameter-based Reynolds number. Now, for a lot of engineering flows, where I mentioned that the Reynolds number, or the Reynolds number you're dealing with is going to be somewhere in the 100,000 range, n equals 7 is a really common first approximation. Right? It's a subset of this velocity distribution has been called the 1/7 power law. But the idea is that, shown here, dimensionless velocity profile, okay, so u over the center line velocity, and r over the radius of the pipe, okay, so 0 to 1, 0 to 1. Our turbulent velocity profile that we solved for analytically using calculus, okay, is shown as this parabolic distribution. And then different values of n, you can see, cause the velocity distribution to flatten out more and more and more and more. So n equals 8, or n equals 6 is this first one, n equals 8 is this one, n equals 10, which would be a Reynolds number out here around 10 million or so. Okay. Or I guess 2 million in this case. You see that that's, as the Reynolds number increases and turbulence intensifies, that's telling us that the turbulence is doing an increasingly good job of pushing those high energy packets of fluid out towards the end of the wall. So the main topic, though, and this is what I wanted to introduce, make sure that we get through today, okay, is the topic of head loss. So in the energy equation, we saw head loss as sort of mysterious h sub L that was given to you. Okay, 2.5 meters of head loss, 1 meter of head loss, ignore head loss, right? But where do those numbers come from? So, cool. All right. I forgot to write down the introduction part here, but so head loss. Right, in our energy equation, we would have P over gamma, P over 1 plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2 plus HL minus HS, right? Where we had our shaft head, we figured out how to calculate this, and we understand where that comes from, but we don't really understand yet where the head loss itself comes from. We do know that it encompasses all of the energy that's wasted on heating, okay, and changes in basically internal energy. So it has to do with thermal losses. Thermal losses themselves come generally from friction. Okay, it's the expenditure of energy overcoming friction. In pipe lab number 3, did the TAs have you guys feel the pipes after about 20 minutes of running? If you had started out the lab and felt the pipe, it would have been cold, room temperature. After about 20 minutes, those pipes are nice and toasty hot. Just from the frictional resistance of the air flowing through them. And you can feel that the rough pipe is hotter, reflecting there's more energy being lost to that thermal element. So this HL, which we refer to as the total head loss, is made up of two components. HL major plus HL minor. So this always cracked me up when I was an undergraduate. I just thought this entire chapter sounded like varying degrees of decapitation. Okay. So you've got major head loss, minor head loss, and total head loss. You add the major head loss and the minor head loss, and you've got your total head loss. we're talking about major head loss today. Okay, and then the video that I'll upload is a short little introduction to minor head loss, which is super simple because it's just values you look up in a table. But the idea here is major head loss is due to friction in straight pipes. And the minor head loss is due to fittings, valves, bends, etc. Basically, this is what occurs in the long lengths of pipe, and this is what occurs locally, where the flow has to undergo some lossy process in a small section of pipe. So in a horizontal fully developed pipe flow, okay, we're going to allow this to be turbulent or laminar, doesn't matter. Oops. We've established, right, that I'm just going to okay. We can say, right, if we take the pressure at one end and the pressure at the other end, so P1, P2, and delta P is equal to P1 minus P2. If we apply the energy equation between these two, we would find that the head loss is equal to delta P over rho G, right? And this is because we know the V1 has to equal V2 and Z1 has to equal Z2. So all of the other terms in the energy equation cancel out. And now this is sort of a recap of the exercise we did at the beginning of the dimensional analysis chapter, where we said, all right, what are all the variables that are going to affect this delta P and therefore the head loss? Delta P, right, is then equal to rho G times the head loss, which we're going to term the major head loss here, which is some function of, right, the length of the pipe, the diameter of the pipe, the velocity of the flow, the viscosity and the density of the fluid flowing through, as well as, okay, and this is what we didn't include before, the height of the roughness elements in the pipe, which we term epsilon. Okay. So, applying dimensional analysis, okay, in the method of repeating variables, what we would get for a dimensionless relationship is delta P over L d over rho V squared is equal to some function of rho V d over mu and epsilon over d. Next, we're going to define this thing called the friction factor. Which is this F equal to 2 delta P over rho V squared times D over L. Okay. Which then could be rewritten in terms of the head loss as 2G
over V squared, D over L times head loss major, okay, which itself then is a function of rho V D over mu and epsilon over D.
So what does this do for us? Well, okay, we've got 3 pi terms, which means that if we conducted a sufficient number of experiments, we could develop, it's possible that we could develop a correlation that allows us to find the value of F, okay, this friction factor, if we know this rho v d over mu, which should look familiar to us, this is our Reynolds number, and then the ratio of the roughness height in the pipe to the diameter of the pipe.
So if we know this guy, and the correlation that relates them to F, then we have a path toward finding what the actual pressure drop in the pipe is, and therefore, or finding the head loss in the pipe, and therefore the pressure drop from one end of the pipe to the other. Okay. So for laminar flow, I'm going to say that F, okay, our friction factor, is a function of, right, the Reynolds number based on diameter and this epsilon over D. Here's the thing.
Laminar flows don't really care about the pipe roughness. The reason for that is because when we talk about the velocity distributions, the flow near the walls in a laminar flow is already much slower moving. So it's less likely to be strongly affected by the presence of roughness on the walls. And so it turns out, if the flow is laminar, this sort of drops out. If, of course, the roughness gets too large, then generally what happens is your laminar flow becomes turbulent flow. And then you don't need to worry about these relationships anyway.
So from our discussion of laminar flow now, we've got that, right, delta P over L is equal to Q over pi r squared times 8 mu. Why did I do that? This should be pi to the 4th here. Okay. And we call this, right, Poiseuille's law. So we can recast this delta P d over 2L, okay, is equal to Q over pi r squared times, we're going to regroup this a little bit, 8 mu over r, and then delta P d over rho L v squared is equal to v over v squared times 32 mu for d rho, and then this all falls out as, F, okay, our friction factor is then delta P over, right, 1/2 rho v squared times d over L is equal to 64 times mu over rho v d, which is equal to, right, 64 over the Reynolds number based on diameter.
Okay, so I went pretty fast through this, but remember when we did laminar flow, we did actually solve for the flow rate through a pipe by integrating our velocity distribution, and we were able to relate that back to the pressure drop, and it gave us this thing called Poiseuille's law, which I said is valid for horizontal pipes. So we just pulled that Poiseuille's law back out, and we said we know how, based on the known distribution of shear stresses in a laminar flow, how that pressure drop is related to the flow rate through the pipe of a given diameter for a flow with a given rho and mu. Then, because that pressure drop in a horizontal pipe is entirely due to major head loss, we plug that in
solved for this friction factor that is a dimensionless variable. Okay, and we end up with this fact that the friction factor is
Equal to 64 over the Reynolds number.
So we can do this theoretically. Okay, this is entirely analytical at this point. Where we stop being able to do it analytically is for turbulent flow. And you guys have seen the solution.
Okay, so we don't have an exact solution for relating the flow rate, the pressure drop, and viscosity in a turbulent flow.
Instead, we use that empirical correlation I was mentioning. Oop, there we go.
Is known as the Moody diagram. And you guys saw this in line number 3. Okay, so x-axis is the Reynolds number based on diameter. That was one of the things we used in laminar flow. The y-axis is our friction factor, and then each one of these curves corresponds to a different ratio of roughness to diameter. All right. Now, which table is this? I forget which table in the book this actually comes from, but there are tables like this all over the place in lots of any kind of book that deals with piping systems, and fluid mechanics book. If you do some Googling, you can find tables like this that have common kind of standard roughness values for different types of pipes at different points in their life cycle. So for example, I guess this one's not shown for different age types, but if you take like a new riveted steel pipe, okay, these are for new pipes, saying that roughness height is generally between 0.9 to 9 millimeters. So any value you could have in between. I'd say that pick 5 millimeters, and you're in that range. And there are other tables that say if that pipe has been aged, if it's 50% of the way through its life cycle, then the accumulation of steel or accumulation of rust and scale might drive that up to 10 to 20 millimeters, etc. The idea is if you know what material your pipe is made of,
You can make a good guess at which one of these roughness heights you use if you know how fast the flow is going through that pipe and what the diameter and the fluid you're carrying is. You can find the Reynolds number, and then by following the curve that corresponds to the roughness and where it intersects with the Reynolds number of your operation, you then move over here and you read your friction factor, and you can find
head loss, and therefore you can plug that into the energy equation or calculate pressure drop directly from it.
So the idea here is once F is known, let's change pen colors here. We know that HL major is equal to F times V squared over 2 times L over GD, and then delta P can be found from the energy equation.
If you don't have the Moody diagram in front of you,
I'm going to write this down. I didn't make a slide for this. So the Moody diagram. If you don't have the Moody diagram in front of you, there are some approximate regressions, okay, some curve fits that people have done to the Moody diagram. And some of them are very, very, very precise. I mean, within percent of any combination of factors there, but they tend to be really hard to apply. A very reasonable, okay, approximation of F comes from known as make sure I'm spelling this right, the Holland equation, which is 1 over square root of F is equal to negative 1.8 log epsilon over D over 3.7 to the 1.1 power plus 6.9 over the Reynolds number. Okay, easy, super intuitive.
But understand that once you have epsilon over d, you have a Reynolds number, this entire side is computed, and then it's fairly easy to solve for f.
Okay. So this is a good one to plug into Excel if you happen to have a pipe of a known roughness, known diameter, known fluid, and you don't want to plot things out graphically. Okay, let's do a couple of examples here. I guess before we hit any examples, any questions on what we just saw? All right. So consider a case. We've got water in a pipe. Right? It flows at Q equal 10 gallons per minute. I know, imperial units. The pipe is a new 0.75 inch diameter galvanized iron pipe. Okay, so here we're going to assume that it's water. We've got 1.94 slugs per cubic foot, and we're going to use kinematic viscosity here, which is 1.21 times 10 to the negative fifth feet squared per second. Remember, if you want the dynamic viscosity, what we've been using most of the time, we just multiply those together. Okay. And here we're asked to find delta P over L, okay, along the pipe. And I should mention that this is a horizontal pipe. So the solution proceeds in a few pretty repeatable steps. First, determine the average velocity through the pipe. Find the Reynolds number. Determine the flow regime. Okay, laminar, turbulent. Which one is it? Find epsilon over d. Find the friction factor F. And then redimensionalize our answer to get the pressure drop. So we've got Q, right, is equal to 10 gallons per minute, which will work out to 0.134 cubic feet, okay, per minute, which is 0.022 cubic feet per second. The area of the pipe, okay, pi d squared over 4 is pi times 0.063 feet, okay, because it's a 3/4 inch pipe. I don't actually have the value written down here. But V bar, okay, is equal to Q over A, which should give us a value of 7.27 feet per second, right? So we've got V bar. Reynolds number, rho V bar D over mu, okay, which is equal to V bar D over nu. Should give us 3.76 times 10 to the fourth. So we've got the Reynolds number. So we got a Reynolds number of about 37,000, laminar or turbulent. that is well into the range of turbulence. Right? It's way bigger than our 4,000 cutoff. So the flow is turbulent, which means that to find the friction factor, we're not going to be able to use that equation of 64 over the Reynolds number. We're going to have to use the Moody diagram or an approximation of the Moody diagram. Okay, so epsilon over d. This is where things get a little bit trickier because we don't know the roughness of the pipe explicitly. Okay, no one's gone in there with what's called a profilometer. It's the thing that measures the surface profile of a flat surface and given us an epsilon. So we have to go back to these kind of out-of-the-book values. Set with a new galvanized iron pipe. Right? So a pipe, galvanized iron, tells us it's got an equivalent roughness of 0.0005 feet, which is obnoxious but usable. Oops, wrong. There we go. Epsilon is equal to 0.0005. Oops. Feet. So epsilon over d is equal to 0.0005 over the diameter of 0.063, which gives us 0.008. All right, so now we've got our Reynolds number, we've got our non-dimensional roughness, we're equipped to go to our Moody diagram. And so 37,000 will put us 1, 2, 3, right about in here. Insert shapes, lines, red. Okay, the our 0.008 roughness puts us, right about here between the 0.01 and 0.005. So we kind of have to interpolate between those two lines. So we would find our intersection oh my gosh. This isn't going well. We'd find our intersection right here. And so from my more careful reading of the Moody diagram earlier, I got that F was approximately equal to 0.037. Okay. So from the Moody diagram, F is equal to 0.037. And in fact, if I applied the Holland equation, that one that I gave you earlier, the Holland equation gives F equal to 0.0369. Okay, so we've got really good agreement between our graphical and our approximate regression. Delta P is then 1/2 rho v squared L over d times F. Which is going to be 1/2, right, at 1.94 slugs per cubic foot times 7.27 feet per second squared times, we want move this down here. We want delta P over L. Delta P over L. So we're going to divide this L over to the left-hand side. 0.063 feet times our 0.037, and we should get delta P over L equal to 30.4 pounds force per foot cubed, okay, which is 0.211 psi per foot of length of pipe.
So the point is here, the Moody diagram or the Holland equation will give you a pretty easily applied method for estimating the
Pressure drop and the length of pipe. Now, as a little preview of what it looks like if you have a combination of pipes. Okay, I want to say, for example, here, let's say we've got, and we'll talk about this more later. Okay, let's say you've got two sections of pipe with a constriction in the middle. Maybe this one's, I don't know, something silly like concrete, and then this one is PVC. So maybe this is like a storm drain system. You needed to figure out the pressure drop from here to here. We've got two challenges. One is we've got two different materials. Okay, we've got the concrete, we've got the PVC, okay, with different diameters. The two different materials mean they're going to have different roughness. We've got different diameters, so we'll have different Reynolds numbers, and then we've got this constriction in the middle. So we would have to figure out head loss major number 1, number 2, and then for this section in the middle, we would have the head loss minor that is due to that constriction. And the sum of all of these three, okay, would give us the total head loss.
So at this point, we know how to get the major head loss for each of these two sections. Okay, that's not too hard. We can solve those independently. And we'll talk about in the video, we'll introduce how to get the minor head loss. It amounts to looking up the table of minor head losses in a book. So let's do another example to close things. Oh, nope, we're out of time. Okay, have a good Thanksgiving, everyone.